This training on heterogeneity of treatment effects is part of the data science training on causal reasoning. I'm Walter Leite from the Research and Evaluation Methodology program of College of Education at the University of Florida. Heterogeneity treatment effects is to understand how treatment varies according to characteristics of the participants. It's important because even though a treatment may have a positive average treatment effect, there could be groups of individuals that are not benefiting as much or not benefiting at all, or even being harmed by the treatment. So traditional evaluation of heterogeneity of treatment effects is done through moderation analysis. So for example, regression analysis, this would be adding interaction terms in the model, interactions between treatment and covariates. However, traditional moderation analysis requires a specific hypothesis about interaction effects, and machine learning can do discovery of heterogeneity of treatment effects without specifying a priori what the hypotheses are about heterogeneity. And this is done by estimating conditional average treatment effects. So, for example, a study that my team at the Virtual Learning Lab presented at the 2023 Learning at Scale conference looked at the heterogeneity of treatment effects of a video recommendation system implemented in Math Nation, which is a virtual learning environment used extensively in Florida. In a large experimental study, the video recommendation system was evaluated and we found a significant average treatment effect. But we also looked at heterogeneity and identified several groups that were benefiting differently from the treatment. And I will show more details later in this presentation. The process of probing heterogeneity of treatment effects goes through multiple steps, and these are some typical steps. One is estimating conditional average treatment effects, visualizing the conditional average treatment effects, obtain variable importance in terms of covariates that relate to or predict conditional average treatment effects, identify those that benefit the most and the least from the treatment, and identify what are the covariate values or group membership for those that benefit the most and the least from the treatment. The conditional average treatment effect is the expected treatment giving a value of the covariate. So here we have an expression of it in terms of potential outcomes. Is the expected value of the difference between the potential outcome if treated and the potential outcome if untreated given specific values of covariates. So the conditional average treatment effect assumes unconfounders, which is met in experimental designs, but for other designs such as propensity score analysis, you would assume that there are no omitted confounders. Also assumes positivity, so none of participants have probabilities of treatment of 0 or 1. So machine learning for estimating conditional average treatment effects includes several different methods. This can be done by pairing a meta-learner and a base learner. A meta-learner is a specific algorithm to estimate the conditional average treatment effect, and there are several of them, such as S-learner, T-learner, R-learner, X-learner. And then a base learner is any supervised machine learning methods, such as random forest, generalized boosting, Bayesian additive regression trees, and neural networks. Here I will just go talk about the two simplest meta learners, the S learner and T learner. To select a meta learner, you would look at how it can be paired with a base learner. Not all meta learners can be based with all base learners. However, there is no empirical way to evaluating the performance. So you can, for example, obtain root mean squared error for the conditional average treatment effect, because conditional average treatment effect is unobserved. There is really no ground truth for applying a meta learner. Now, there are simulation studies such as Carroll's study that found that Bayesian causal forest and multitask Bayesian processes work better, but this is a field that still needs a lot of work. The S-learner uses a single model to for the treated and control groups. So the inputs are the outcome, the treatment assignment indicator, and covariates, which are xi. You start by regressing the outcome on the covariates and the treatment assignment indicators. Then you use that model. And here by regress, I mean you can use any supervised machine learning method. So this is where the base learner would go, like you could replace step one by any base learner. So could this be done, for example, by random forests? And then step two, you use the model trained to estimate potential outcomes in the absence of treatment, given the value of covariates. In step three, you estimate potential outcomes given the presence of treatment and the values of covariates. So the potential outcomes for those, for if all participants were treated, right? And then the conditional average treatment effects are the difference between the mean of the potential outcomes if treated and the potential outcomes if not treated, conditional or covariates. The weaknesses of the S-learner is that it uses the same model, the same model for both treated and control groups, and but they may have different relationships with covariates, and it doesn't adapt to differences, sparsity, smoothness across groups. The T-learner tried to solve this model by having a separate model for treated and untreated. So here, in the first step, you select only the untreated and regress the untreated outcomes on the covariates. So by regress, I mean fit a supervised machine learning model only to those that are not treated. In the next step, you fit a supervised machine learning model to just that to those that are treated, and that is done to predict treated outcomes. Then you estimate the potential outcomes for the entire sample if not treated, given covariates, and then you estimate the potential outcomes for the entire sample if treated, given covariates. And then you obtain the conditional average treatment effect, which is the difference between the potential outcomes if treated and potential outcomes if not treated, given covariates. Because in the T-learner, because you using different models for the treated and untreated, you are not allowing the sharing of information across groups. And if one of the groups is much smaller, you may have unreliable estimates of the conditional average treatment effect. A different approach is generic machine learning, also known as generic ML. So this approach doesn't focus on estimating the conditional average treatment effect, but on estimating summaries of it: the best linear predictor, the sorted group average treatment effects, gates, a classification analysis clan. It can be used with any supervised machine learning model, and but it assumes that treatment was randomly assigned. So current version of generic ML cannot accommodate studies that are not experimental. But there are other types of meta learners, such as the R learner, that can easily accommodate, for example, inverse probability of treatment weights in propensity score analysis. So in generic ML, the best linear predictor is to use original least squares regression with the, so this is just a bivariate regression where the outcome is the conditional average treatment effect, the predictor is the baseline conditional average, and in this model you are not really as interested in predicting the conditional average treatment effect, but you are interested in the regression coefficients. The intercept beta 1 is the average treatment effect, and the slope beta 2 quantifies treatment effect heterogeneity. So if that slope is not statistically significant, there is no heterogeneity of treatment effects. You can stop here. However, if it's significant, then you would proceed to the next step to identify how the treatment varies across groups, given covariates. The sorted group average treatment effects, or GATES, is to sort the distribution of conditional average treatment effect into groups that explain as much of the heterogeneity as possible. So these groups here, you can have a different number of groups, but here it's 5 groups, where group 1 benefits the least from the treatment and group 5 benefits the most. So here I have an example from the video recommendation system. So this is from that paper presented in the Learning at Scale conference in 2023 that I mentioned earlier. And group 1, the average treatment effect for group 1 is actually negative. So they not only did benefit, they did worse if they were treated. And same thing for group 2, group 3 did not benefit. And then group 4 and 5, they had a positive average treatment effect for the video recommendation system. So the difference between group 1 and group 5 and group 1 is 1.098, so it's a large number. So there was a lot of heterogeneity here in the effect of the video recommendation system. Now, classification analysis is to identify variables, covariates that relate to the heterogeneity. So you estimate the means of covariance. So this is done by reversing the dependent and independent variables. So this is not an ANOVA, but it's similar. So the covariates become the dependent variable. So if you have 90 covariates, you would look at 90 different analyses, and the factor are the group average treatment effect that I showed in the previous slide. So this is mostly a visual analysis. You can, for example, look at the mean differences for the various values of covariates or calculated effect size, such as a pseudo eta squared for each covariate and sort them, and then understand which and look at which variables have the largest difference. You can focus on a single difference, which would be the difference for each covariate between the group that benefits the most and benefits the least, and sort those differences. And that's what we did in the example paper. So we found that teachers of so for those that benefit the most were teachers that used video more than other features, spend more time in Math Nation and monitor students on the teacher dashboard, and those benefited the least used assessment more, had the math professional, social and professional development needs, and struggle to engage students. Now, this was not inferential because we just calculated the difference for each covariate between the group that benefited the most and the group that benefited the least, and they ranked. There isn't inferential statistics here, but could be applied, although you would, if you, for example, ran a formal ANOVA, you would have to do control of type 1 error rates or false discovery rate because there are so many covariates, right? And you would, the family-wise type 1 error rate would be inflated. So here's some references for further reading. This paper by Caron reviews meta-learners and does a small simulation study comparing them. And the Cherozokov paper, it's a very technical paper, but presents the generic ML method. But it does have an example. After the technical presentation and the proofs, it does have an example that's very interesting.